1996. A spacecraft is moving through the dark on the far side of Jupiter, the first machine humanity has ever placed in orbit around the largest planet in the solar system. It has just swung in close over one of Jupiter's moons. And in that moment, one of its instruments picks up a sound. It is a sound no one has ever heard before, a thin, rising whistle, a wash of crackling static. It is the voice of a magnetic field, and it is coming from the moon itself. Now, that should not be possible. Magnetic fields like this come from planets. They come from worlds with hot, churning metal in their hearts, the way the Earth does. A moon is supposed to be a cold, dead, silent thing. This one is humming, and the more you look at it, the less it behaves like a moon at all. It is the largest moon in the entire solar system, bigger than the planet Mercury. It has a core of metal, a deep ocean, and layers of rock and ice stacked one on top of another, exactly the way a planet is built. If this object orbited the Sun on its own, we would not hesitate for a second. We would call it a planet. But it doesn't orbit the Sun, it orbits Jupiter. So, we filed it away as just another moon, a servant in the giant's shadow, and we even named it for one. Because the world is called Ganymede. The name was always a confession. Jupiter took something that didn't belong to it. We just never said it out loud. It took a passing spacecraft and a sound no one had ever heard to remind us what's really out there. Not a moon, a captured world. Still alive in the dark, humming a magnetic heartbeat that no moon was ever supposed to have. Ganymede orbits Jupiter once every 7 days, locked so that the same face always points toward the planet, the way our own moon always shows us the same side. By that definition, it's just another satellite. But look closer, and the word moon starts to feel too small. In January of 1010, the Italian astronomer Galileo Galilei pointed a crude telescope at Jupiter and noticed 4 tiny points of light arranged in a line beside the planet. Night after night, they shifted position. They were not stars, they were worlds, circling something other than the Earth. It was the first time in human history that anyone had seen a moon orbiting a planet that wasn't ours. And it cracked open a very old idea, the idea that everything in the heavens revolved around us. Those 4 points of light helped end that idea forever. The largest of them was named after a figure from Greek myth. Ganymede was said to be a beautiful young boy, carried up to Olympus by Zeus, the god the Romans called Jupiter, who had disguised himself as an eagle. Up among the gods, Ganymede became their cupbearer, a servant, always close to the king, always in his shadow. It is a fitting name, because for 400 years that is exactly how we treated this world, as a servant of Jupiter, a thing in the shadow of something bigger. We were wrong about that too. The first sign came from that magnetic field in 1996. Because a magnetic field is not a small thing. It's a message from the inside of a world. And the message Ganymede was sending told us that, somewhere deep beneath all that ice, something was still alive in the geological sense, still hot, still generating power. A dead world doesn't do that, and Ganymede, by every reasonable expectation, should have been dead a very long time ago. So the question became simple to ask, and almost impossible to answer. Why is this moon still awake? To understand why that question is so hard, you have to understand a fight that has been quietly going on among scientists for decades. And to understand the fight, it helps to meet the person who finally named it out loud. His name is Kevin Trin. He's a planetary scientist who earned his doctorate in 2025 and now studies the insides of distant worlds at Caltech. And his whole job, in a sense, is to read those messages from the deep, to take a faint signal picked up by a passing spacecraft and work backward to what's happening thousands of miles below a frozen surface he will never touch. Trin says it plainly. A dynamo, that internal engine that makes a magnetic field, is one of the only tools we have for understanding what's happening deep inside a body, using nothing but data sent home from a spacecraft. It's like listening to a heartbeat through a closed door. You can't see the heart, but you can hear that it's beating, and from the rhythm, you can guess an enormous amount. Now here is the contradiction Trin kept running into. And it's the kind of contradiction that, once you see it, you can't unsee. On one side, you have the people who study how Ganymede makes its magnetic field. For their models to work, Ganymede needs a metal core that formed early, about 4.5 billion years ago, around the same time the moon itself was born. A hot, ancient heart, slowly cooling ever since. On the other side, you have the people who study how Ganymede formed in the first place. And their work says something completely different. It says Ganymede was probably born cold, too cold in fact, to ever separate out a metal core at birth at all. Sit with that for a second, because this is the whole story in one sentence. One group of scientists needs Ganymede to have built a metal core right at the start. Another group of scientists says it was far too cold to do any such thing. As Trin put it, both of these things cannot be true at the same time. For decades, these two fields of research moved forward in parallel, side by side, each making its own assumptions, rarely stopping to notice that their assumptions flatly contradicted each other. It's a strange thing about science. Sometimes a contradiction can sit in plain sight for years, simply because no one is standing in the spot where both sides are visible at once. Trin decided to stand in that spot. And in May of 2026, he and his colleagues published what they found in the journal Science Advances. The paper has a quiet, technical title, Powering Ganymede's Dynamo with Protracted Core Formation. It does not sound dramatic, but the idea inside it is one of the strangest a planetary scientist has proposed in a long time. The idea is this: what if Ganymede's core never finished forming? What if it is still forming right now today? Let's slow down and look at exactly what we found, because the strangeness only deepens the closer you get. A magnetic field, the kind that Earth has and the kind Ganymede has, is made by something called a dynamo. The word sounds complicated. The idea is not. Take a fluid that can conduct electricity. Molten metal works perfectly. Now set that fluid in motion. Stir it, churn it, make it rise and fall. As that conducting fluid moves, it generates electric currents, and those electric currents, in turn, generate a magnetic field that wraps around the whole world. Motion becomes electricity, becomes magnetism. That's a dynamo. On Earth, this happens in our core. We have a solid ball of iron at the very center, and around it, a vast shell of liquid metal. That liquid churns in slow, rolling motions. Picture the blobs, rising and falling in a lava lamp, only made of molten iron and the size of a planet's interior. That churning is what makes Earth's magnetic field. It's the reason a compass needle points north. It's the reason we have auroras. Plenty of worlds run this engine. Mercury does it. Earth does it. The giant planets Jupiter, Saturn, Uranus, Neptune all do it. Big planets, made of the right stuff, with hot interiors. That makes sense. But here is the surprising fact, the single strangest thing in this entire story. And it deserves a moment to land. Out of more than 300 known moons in our solar system, Ganymede is the only one that runs this engine. The only one. Not Europa. Not our own moon. Not the giant moons of Saturn. Just this one. A single frozen satellite, alone among hundreds, with a working magnetic heart. And we measured it. The field Ganymede makes is faint at its surface. It reaches a strength of roughly 720 nanotesla. That's a small number, but it isn't zero. And for a moon, zero is what it's supposed to be. So, what does that mean? It means that deep inside Ganymede, beneath an ocean and miles of ice, there is metal in motion. There is an engine still turning. And the obvious question is the one that bothered Trin the most. Why this moon and no other? Because Ganymede did not form alone. It formed in the same swirling disk of leftover material that built Jupiter's other large moons, all of them condensing out of the same cloud at roughly the same time. Right next door is Callisto, almost the same size as Ganymede, almost the same density, in a neighboring orbit, practically a twin. And Callisto shows no sign of a dynamo at all. Two worlds born side by side from the same material in the same place. One has a magnetic heartbeat, the other is silent. Why are they so different? That difference is the thread this whole investigation pulls on. To see why Ganymede's heartbeat is so shocking, you have to understand the normal life story of a planetary core, because cores, as a rule, are not supposed to last. It goes like this. When a world is forming, it does so by accretion, by smashing together smaller and smaller chunks of rock and metal and ice, building up a body piece by violent piece. All of that smashing generates heat. If a forming world gets big enough, or forms fast enough, it gets hot enough to melt. And when the inside of a world melts, something elegant happens. The heavy stuff, the iron, the metal sinks. It pools down toward the center and forms a dense metallic core separated from the lighter rock around it. Scientists call this differentiation. It's like shaking a jar of oil and water and watching them sort themselves into layers. The metal goes to the middle. Now, there's a clock on all of this. Some of the heat comes from a special ingredient, a radioactive form of aluminum, aluminum-26. In the very early solar system, this isotope was abundant, and it was powerful. As it decayed, it pumped out heat. Even small bodies that formed early enough to scoop up a lot of it could get hot enough to melt their metal and build a core. But aluminum-26 has a short life. It burns through itself quickly. So this whole window, the time when a world can build a metal core using the heat of its birth, slams shut early. Conventionally, scientists think core formation finishes during a world's accretion, or within the first 1 to 200 million years after the solar system itself formed. For scale, our solar system is now around 4.5 to 4.5 billion years old. So that core building window? It closes in roughly the first few % of solar system history. After that, the door is shut. And then comes the long decline. The core, once formed, slowly cools. For a while, that cooling keeps the metal churning and the dynamo running. But eventually, the core gets too cold. The churning stops, the metal solidifies, and the magnetic field switches off, like a heart that finally stops beating. This is the normal fate. Look around and you'll see it everywhere. Our own moon has a cooled core. It probably ran a dynamo once, long ago. Today it makes no magnetic field of its own. It went quiet. Even Mars, a world only a little larger than Ganymede, went through this entire process and came out the other side. Mars built a core, ran a dynamo, and then the engine died. Today Mars has no internally generated magnetic field. It's a planet that already finished the story. So by every rule we know, Ganymede should be in the same condition. A frozen moon, smaller than Mars, far from the sun, born billions of years ago. Its core should have formed early, if it formed at all. It should have cooled, and it should be dead. Instead, it's running. Right now. Today. That is the fact that doesn't fit. And when a fact doesn't fit, you have two choices. You can ignore it, or you can ask whether one of your rules is wrong. For a long time, the way scientists explained Ganymede's stubborn heartbeat was a model called iron snow. And it's a beautiful image, so it's worth picturing. In this model, Ganymede has the kind of core we'd expect, an old metal core, formed early, slowly cooling. But near the top of that core, where it's coldest, the liquid iron begins to crystallize. Tiny flakes of solid iron form, like snow. And because they're heavier than the liquid around them, they sink. They fall through the molten core, down toward the center, where it's hotter, and there they melt again. Snow that falls, melts, and rises to fall again. That endless churning is what keeps the dynamo alive. It's an elegant idea, and for years it was the best explanation we had. But it rests on one assumption. It assumes Ganymede started out hot enough, early enough to build that metal core in the first place. And that's exactly the assumption the formation scientists say is wrong. Here is their case. Ganymede is an icy moon. Icy moons, the thinking goes, formed relatively late and relatively cold, late enough that most of that powerful aluminum-26 had already decayed away, so there wasn't much of it left to provide heat. And Ganymede, for all its size, is still small compared to a planet, too small to melt itself with the heat of accretion alone. The temperatures in the disk where these moons were born are thought to have been only a couple of 100 degrees above absolute zero, far too cold to melt metal. Many icy moons may never have gotten warm enough to even melt their own water ice. And right next door, Callisto, Ganymede's near twin, is often thought to be only partially sorted out inside, never fully differentiated. A world that mixed its ice and rock and never finished separating them. So if Callisto stayed cold and mixed, why would Ganymede have been any different? They came from the same place. This is where Trin and his team did something simple and bold. They stopped assuming Ganymede was born hot. They built a model of its interior that started cold, a uniform temperature of around 250 Kelvin, with the rock and the metal mixed together, no core at all. A cold start. And then they let it warm up, slowly, over billions of years. What warms it? Three things, working patiently. There's the steady decay of radioactive elements, not the quick-burning aluminum, but the long-lived isotopes that release their heat over eons. There's the gravitational energy released as material rearranges inside. And there's tidal heating, the flexing and squeezing that Jupiter's gravity inflicts on the moon. That tidal squeezing matters. And it matters because of a relationship Ganymede has with its neighbors. Ganymede, Europa, and Io are locked in a gravitational rhythm called the Laplace resonance. For every single time Ganymede circles Jupiter, Europa goes around twice and Io goes around 4 times. They line up over and over, tugging on each other in a perfect repeating pattern. That pattern keeps their orbits slightly stretched, slightly oval, and a moon in a stretched orbit gets flexed by its planet's gravity, kneaded like dough, and that flexing makes heat. In Ganymede's distant past, that heat may have been strong enough to leave a visible mark to help create the bright, grooved scars we still see written across its surface today. So, picture it, a moon that begins as a cold, undifferentiated mixture of ice, rock, and metal. And then, over billions of years, it very slowly begins to warm from within. And keep that image in your mind, because something is going to happen to it. Not quickly, not violently, but inevitably. Watch what happens when a slowly warming world finally crosses a certain temperature, because that's where this story turns. Inside Ganymede, the model assumes the metal is a particular mixture iron, combined with iron sulfide. Scientists pick this combination for a careful reason. An iron and iron sulfide mix melts at a lower temperature than pure iron alloys do. So if you're trying to find out whether a cold moon could ever melt its metal at all, this mixture gives you the gentlest, most conservative case. If it can't melt this, it can't melt anything. This mixture has a special temperature, a melting point of about 1250 Kelvin. Below it, everything stays solid and mixed. At it, the metal begins to melt. So, here's what the warming model shows, step by patient step. For the first stretch of Ganymede's life, the warming is actually fairly fast. But then it slows, because the heat runs into an obstacle. The rocks inside Ganymede are hydrated, they have water locked into their very structure. And as the interior warms, somewhere between 200 million and 1.5 billion years after the moon formed, that water gets baked out of the rock. Driving water out of rock soaks up enormous amounts of energy that would otherwise have gone into raising the temperature. So the warming stalls while the rock gives up its water. But the heat sources don't quit. And after that stall, the temperature keeps climbing. In the team's central example, somewhere around 2.5 billion years after Ganymede finished forming, the interior finally reaches that melting point, and the metal begins, at last, to melt. Now watch closely, because this is the heart of the whole idea. When the metal melts, it's denser than the rock around it. So droplets of liquid iron begin to sink. They trickle downward through the moon's interior, gathering at the center, slowly building a core that did not exist before. A core being born not 4.5 billion years ago, but late, and not all at once, but as a slow, steady drip. And here is the part that makes a dynamo possible. That falling iron doesn't just pile up quietly. As fresh metal rains down onto the growing core, it stirs the liquid that's already there. The very act of building the core sets the core in motion. And motion in conducting liquid metal, that's the recipe for a magnetic field. This is the new idea. The team calls it a warming-driven dynamo, and it is the mirror image of everything that came before. The old models all needed a core that was cooling, a finished, ancient core, slowly losing its heat, and using that cooling to drive the churning. Tringe's model needs the opposite. It needs a core that is warming and growing. The stirring doesn't come from heat leaving, it comes from new metal arriving. A cooling dynamo is a heart winding down. A warming dynamo is a heart still being built. And in their simulations, this construction doesn't finish. The drip keeps dripping, the core keeps growing, the stirring keeps stirring for billions of years, all the way up to the present. Which means that if this is right, the engine we detected in 1996 isn't the dying ember of an ancient fire. It's a world still being assembled, caught, frozen mid-sentence, in the act of becoming. If that's true, then Ganymede would be the only known place in the entire solar system where the formation of a metal core is still happening. A process we always thought belonged to the deep past, to the first violent moments of a world's life would be unfolding, right now, inside a moon we can point a telescope at. Now, a good scientist doesn't fall in love with a beautiful idea. A good scientist tries to break it. So Tringe team ran the model again and again, not once, but 1,000 times. Each run, they changed the dials. How fast did Ganymede form? How much water was in its rocks? How much tidal heating did it endure in its youth? They wanted to know how often this warming-driven dynamo actually shows up, or whether they'd just gotten lucky with one lucky set of numbers. The answer was encouraging. In the batch of simulations with no extra tidal heating in the rocky interior, the warming-driven dynamo succeeded in about 69% of cases. 241 out of 349 runs produced exactly what we see at Ganymede today. Not a fluke, a common outcome. But the experiment revealed something else, something almost poetic. To end up like Ganymede, a world has to thread a very narrow path. If it warms too slowly, the metal never reaches its melting point. The iron never separates, the core never starts to form, and there's no dynamo at all. The world just stays a cold, mixed lump. But if it warms too quickly, if it had stronger tidal heating or more radioactive material early on, then it would have melted its metal and finished building its core long ago. The drip would be over. The construction would be complete. And the warming-driven dynamo would have shut down billions of years in the past. So Ganymede has to live in between, warm enough to melt its metal, but slow enough that the job still isn't done. Too cold and nothing happens. Too hot and it's already over. Ganymede, somehow, is right in the middle, still cooking, still in progress. That's a strange and humbling thing to consider. The reason this moon is the only one of its kind might simply be that it found the one narrow lane where a core could still be forming today and stayed in it for billions of years by something that looks an awful lot like luck. And it might explain the twin. It might explain why Callisto is silent. Callisto, in these models, probably took the colder road forming later, or with a higher proportion of ice, or simply too small and too cool to ever start melting its metal. Same neighborhood, different path. One world crossed the threshold, the other never did. Now, all of this drama is happening at the very center of Ganymede. But to reach that center, you'd have to pass through one of the most extraordinary structures in the solar system. Because Ganymede is built in layers, like nothing on Earth. At the heart, the metal core, the one that may still be forming. Around it, a thick shell of rock. And around the rock, a vast shell of ice. The surface you see is just the frozen top of that outer shell, but it is not all ice. Buried inside that shell, hidden under miles of frozen crust, is an ocean. Scientists first suspected it back in the 1970s, working only from models of what such a large moon should be like. The 1996 magnetic field measurements added support. And then, the Hubble Space Telescope delivered the best evidence yet by doing something genuinely clever. Remember those auroras? The glowing ribbons of charged gas circling Ganymede's poles, lit up by its magnetic field. A team led by Joachim Sauer of the University of Cologne in Germany realized those auroras could be used as a probe. As Jupiter's own magnetic field shifts, Ganymede's auroras rock back and forth in response. And how much they rock depends on what's underneath the surface. A hidden ocean of salty water which conducts electricity would push back against the changing field and dampen the rocking. So Sauer's team watched the auroras rock. And from the size of that rocking, they confirmed it. There's an ocean down there, and it is not a small one. Ganymede's hidden ocean is estimated to be around 60 miles deep, roughly 10 times deeper than Earth's ocean, buried beneath a crust of mostly ice, about 95 miles thick. It's thought to hold more water than all the water on the surface of the Earth, combined. An entire ocean, more water than our whole planet's seas, sealed in darkness under a frozen sky. But here's the strange part. That ocean might not be a single, simple layer. In 2014, a NASA team led by Steve Vance at the Jet Propulsion Laboratory modeled what happens to water under the crushing pressures inside Ganymede. And they found something almost absurd. The ocean might be stacked ocean, then ice, then ocean, then ice in multiple layers. They nicknamed it the club sandwich. The reason is that ice is weirder than you think. The ice in your drink is the lightest kind, and it floats. But squeeze water hard enough, and its ice crystals pack together into denser and denser forms, so dense that at the bottom of an ocean like Ganymede's, the ice actually becomes heavier than the water and sinks. Vance described it like rearranging shoes in a suitcase to fit more in the molecules just learn to pack tighter. And it gets stranger still. In one of the upper layers, the team found that the ocean might snow upward. As the water churns, ice forms in the middle of the ocean. And when that ice forms, it pushes out the salt dissolved in the water. The salty leftovers, now heavier, sink while the fresh, light ice floats up. Snow, rising instead of falling, in an ocean that has ice both above it and below it. It's a long way from the simple picture of a frozen moon. And we have direct hints that this ocean is interesting chemically, too. In 2021, NASA's Juno spacecraft flew close to Ganymede and detected mineral salts and organic compounds on its surface, the kinds of ingredients that, on Earth, are tied to the chemistry of life. Wherever water and rock meet, scientists pay attention, because on our own world, that meeting place, deep on the dark ocean floor, may be where life itself began. Come back up now, all the way to the surface, because even the skin of this moon tells a story. Ganymede's surface is split into two completely different kinds of terrain, and the contrast is impossible to miss. About 40% of it is dark, ancient, heavily cratered ground, battered over billions of years. The other 60% is bright, and it's covered in something stranger: long, parallel grooves, ridges, and furrows running for thousands of miles across the moon, some of them standing as tall as 700 meters. When scientists studied images from the Voyager probes decades ago, they realized something. The bright, grooved terrain seems to have grown, spreading out, taking over the older, dark terrain, converting it. The lines weren't random. They were the signature of tectonics of a crust that was pulled, stretched, faulted, and rearranged. An early chapter, written in ice, of plates rifting and sliding past one another, the way continents do on Earth, but on a frozen world. And there's a small detail that says a lot about what this surface is made of. The big craters on Ganymede are mostly flat. On a rocky world, a crater stays sharp and deep. But on Ganymede, the ground is soft enough, icy enough, that over time, the craters slowly settle and flatten out, like footprints relaxing in slush. The surface remembers, but only for so long. Above all of it, there is the thinnest breath of an atmosphere. The Hubble telescope found evidence of a faint oxygen atmosphere around Ganymede oxygen that seems to come off the icy surface itself. Don't picture anything you could breathe. It's a whisper, almost a vacuum, but it's there. And it is cold, brutally cold. Daytime surface temperatures on Ganymede run from about 90 to 160 Kelvin, in more familiar terms, somewhere between roughly 297 and 171 degrees below zero on the Fahrenheit scale. The Sun, out here, is a distant thing. Jupiter and its moons receive less than 1/30th of the sunlight that reaches Earth. Sunlight that takes about 43 minutes just to cross the gulf from the Sun to this part of the solar system. So stack the whole picture up. A frozen, scarred surface, breathing the faintest trace of oxygen into the dark. Beneath it, an ocean deeper than any on Earth, possibly stacked in layers, snowing upward in the black. Beneath that, a shell of rock. And at the very center, in the deepest dark of all, a metal core that may still be forming, stirring itself into a magnetic heartbeat we can hear from 100 million miles away. That is one moon. We just call it a moon. To really feel how unusual Ganymede is, it helps to look at the worlds right beside it, the other large moons Galileo spotted in 1010, because they all formed together, and yet each one went its own way. Closest to Jupiter is Io. Io took the opposite path from a frozen world. It is the most volcanically active body in the entire solar system, a place of hundreds of volcanoes, some flinging fountains of lava miles into space. Squeezed mercilessly by Jupiter's gravity, Io is dry and molten and furious. It kept no water at all. Next is Europa. Europa is smaller, and it's mostly rock with a relatively thin coating of ice. Only a few % of it is water by mass. But beneath that ice sits a salty ocean, and Europa is one of the most promising places in the solar system to search for life beyond Earth. It may have warmed up more than Ganymede did in its history, and in the warming-driven model, a moon that ran hotter early on would likely have finished building its core long ago, which could be exactly why Europa, today, shows no clear dynamo of its own. Then comes Ganymede, and then, farthest out of the four, Callisto. Callisto is the puzzle that won't go away. It is the most heavily cratered object in the solar system, a surface so ancient and untouched that it's like a frozen record of the early solar system. And in size and density, it is almost a copy of Ganymede. Two large moons, nearly identical, in neighboring orbits. But here is the conundrum that has bothered scientists for years. Callisto appears to be only partially sorted out inside its ice and rock, never fully separated into clean layers. And Callisto has no obvious magnetic dynamo. There's also a small clue in the way the moons are arranged. Io, Europa, and Ganymede are locked in that tidy, resonant rhythm, but Callisto sits outside it, dancing to no one's beat but its own. So why are the twins so different? In the warming model, the answer is that Callisto likely walked the colder road. Forming later, or carrying more ice, or simply staying too cool, any of these could have stopped its metal from ever melting. Ganymede crossed the threshold. Callisto didn't. Same raw materials, same corner of the solar system, two completely different fates. And zoom out one more step to the broader rule. Earth runs a dynamo. Mercury runs one. The giant planets run them. But our moon's dynamo died. Mars built a core and ran a dynamo and then went silent. A world that finished the whole story and now drifts on without a magnetic field. Against all of that, against the rule that cores form early and engines eventually die, Ganymede stands alone, the one moon. The one world we know of that might still be building itself from the inside out. It really does begin to look less like a servant in Jupiter's shadow and more like a planet that got caught and kept. Now, it's important to be honest about where this story actually stands, because the warming-driven dynamo is an idea. A careful, well-tested, beautifully argued idea, but an idea all the same. And Trin himself is the first to say so. His team's results do not rule out the older picture. It's still entirely possible that Ganymede has a finished, ancient core that is cooling and churning in the conventional way. What the new work shows is that there is another explanation, one that fits the awkward fact that Ganymede was probably born cold. The team isn't claiming to have closed the case. They're saying the case was never as closed as everyone assumed, and that more work is needed to decide which mechanism is really at play. Other scientists agree the idea is worth taking seriously while keeping a careful distance. One reviewer, a planetary scientist at the University of Münster, noted that if the still-forming core turns out to be the answer, then people may have to rethink how they understand magnetic field generation altogether. Another, at the German Aerospace Center, found the story interesting and reasonable, but admitted she wasn't fully convinced the team had accounted for every possible effect with so many variables in play. That caution is fair. So how do you test an idea about the deepest interior of a moon you can't drill into? You go there. And remarkably, the spacecraft that may settle this is already in flight. In April of 2023, the European Space Agency launched a mission called JUICE, the Jupiter Icy Moons Explorer. It lifted off from French Guiana on an Ariane 5 rocket, a 6,000-kilogram machine carrying 10 scientific instruments, bound for the outer solar system on an 8-year journey. It has not taken a straight path. To build up enough speed, JUICE has been slingshotting through the inner solar system, stealing momentum from planets. It swung past the Earth and Moon together in 2024, the first spacecraft ever to use both at once. It flew by Venus in 2025. Along the way, in late 2025, it even turned its cameras on a visitor from beyond our solar system, the interstellar comet that swept through that year, and sent home images of an object that came from another star. JUICE is scheduled to swing past Earth again in 2026, and once more in 2029, before finally arriving at Jupiter in 2031. And then, in 2034, it is set to do something no spacecraft has ever done. It will enter orbit around Ganymede itself, the first time in history that any spacecraft will orbit a moon other than our own. And this is where the test comes in. A planetary geophysicist at the Johns Hopkins University Applied Physics Laboratory pointed to exactly what JUICE could reveal. By measuring Ganymede's gravity field in fine detail, the spacecraft can map how mass is arranged deep inside the moon. If the iron is already gathered into a tight, finished core at the center, that's one signature. If the metal is still spread out, still mixed through the interior, still in the middle of sinking, that's a completely different signature. JUICE carries the instruments to tell those two stories apart. A magnetometer to measure the field with new precision. radar that can see as deep as several miles into the ice, spectrometers to read the surface chemistry. Together, they could finally show us whether Ganymede's heart is finished or still being made. So let's come back to that moment in 1996, when a falling spacecraft's instrument registered something it wasn't supposed to find. A magnetic field around a moon, where there should have been only silence. For 30 years, we've known that signal was real. We just didn't know what it meant. We assumed it was an echo, the dying warmth of a core that formed in the chaos of the early solar system and has been cooling quietly ever since. The last heat of something very old. But maybe we had the direction wrong. Maybe that signal isn't an ending. Maybe it's a beginning still in progress. Maybe, when we listen to Ganymede's magnetic heartbeat, we aren't hearing a fire going out. We're hearing a world that hasn't finished being born iron, still falling through the dark, gathering at a center that grows a little larger with every passing eon, stirring itself into life 4.5 billion years after it began. And the strange, wonderful thing is that we don't know which it is. Not yet. We have a model that says one thing and a model that says another, and both of them might be partly right. The whole question hangs on what's happening thousands of miles beneath an ocean we can't reach, on a frozen moon we have visited only in passing. There's something humbling in that. We have stood on this idea for 400 years, the idea that we understand our own backyard, that the solar system is mapped and labeled and known. And then a single moon, a thing we filed away as a servant of Jupiter, turns out to be doing something we have never seen anywhere else. Possibly still assembling itself, in slow motion, in the cold and the dark, while we argue about how. We launched the rocket. It is out there now, falling toward Jupiter the way the last one did, carrying instruments built to settle the question. In a few short years it will arrive and slip into orbit around this moon, and look down into it harder than anyone ever has. And for the first time, we may learn whether we have been watching an ending or a beginning all along. Until then, all we can do is listen to a faint magnetic pulse from the largest moon in the solar system and admit that the more closely we look at the things we thought we understood, the stranger and the younger and the more alive they turn out to be.